So I'm speaking here from IBM Research Almaden in San Jose, California. I will describe to you Synapse Project, which is the aim, the quest to engineer brain-like computing facility in modern CMOS. So the human brain has amazing power. Given an object such as a rose, it can extract from it its appearance, its smell, texture, taste, and sound. And it can transcribe all these different sensory modalities into uniform language of neurons firing on and off. And it can then actuate motor modalities such as speaking, picking it up, walking to it, and it can do so while consuming less power than a light bulb and occupying less volume than a 2-liter bottle of soda. It is our goal in the Synapse project to create a new computer that mimics brain's ability to deal with high-dimensional, diverse, variable, multisensory data. Now, computers and the brain are very different and complementary. Today's computers, on one hand, run at 5 gigahertz speed. The brain is 10 hertz, about 1 billion times slower. Today's computers are sequential, the brain is parallel. Today's computers are linear, the brain is high fan out. On one hand, the computers are clocked, the brain is event-driven or asynchronous. The power density of today's computers is about 100 watts per square centimeter. The brain has a power density of 10 milliwatts, 4 magnitudes, orders of magnitude off. And most fundamentally, today's computers separate memory from computation via communication. But the brain integrates memory, computation, and communication. So it is not possible to build efficiently brain-like functionality using today's computers. And doing so would require essentially a power budget equivalent to a city, whereas this thing consumes 10 to 20 watts. So our goal in the DARPA SyNAPSE project is literally to build a brain in a box, a computer with 100 trillion synapses that fits in 2 liters and consumes 1 kilowatt of power and operates in real time. So how do we go about this challenge? We have brought together far-flung disciplines of neuroscience, supercomputing, and nanotechnology to create an entirely new field called cognitive computing. Today, I'll give you a flavor of each of these 3 areas and our results in it. What you see on the screen is the largest long-distance wiring diagram in the primate brain. Different colored patches are different areas in the cortex as well as subcortex of the monkey brain. Different white wires are long-distance wide connectivity. This connectivity diagram has 383 brain regions and 6,602 connections, and it allows us to understand the brain as a network, as a graph, and it allows us to lay the blueprint of a new generation of future computers. Now, using this blueprint, which gives us neuroanatomical substrate, structural substrate, we have now designed a neurophysiological substrate, a neuron. We have designed a very simple neuron that requires very few gates to implement. So it can be implemented very efficiently in hardware. And yet, it has a rich variety of biologically observed behaviors, biologically relevant behaviors. So from neuroscience, we extracted neuroanatomy and neurophysiology, which are the two sister subfields that make neuroscience. From there, what we did is 2 years ago, we announced a tiny little chip. We call it a neurosynaptic core. This chip has 256 neurons, which is roughly the same scale as number of neurons in a worm brain. And we built two versions of this chip. One is field programmable and one is field adaptable. And using this chip, we have demonstrated a variety of simple applications, such as playing Pong or digit recognition, using just 256 neurons. So next step in designing a brain-like computer is to use these neurosynaptic cores as tiny little building blocks, as modules, and then to create the next generation architecture based on this cores as a network of neurosynaptic cores. So imagine a huge tiled array of neurosynaptic cores, each core consisting of 256 neurons, 256 axons, these axons connecting to neurons via 256 times 256, which is 64,000 synapses, and this core connected with other cores to form essentially unlimited scaling in architecture. Now, this is very different than traditional computers. First, it integrates memory, computation, and communication. Second, it's parallel. All the cores can operate in parallel like the brain. Because it's parallel, it's also distributed. There is no clock in this architecture. It is asynchronous or event-driven. Things happen when they need to and only when they need to. It operates at a very slow speed, unlike today's computers, which operate at gigahertz. It is fault tolerant. Some of the neurons can die, some of the synapses can die, some of the connections can die. It'll still continue to give you some degree of operation. And it is feasible to implement in today's CMOS technology, which then serves as a beacon for future new technology itself. Now we have taken this architecture and we have then taken one of the world's largest supercomputers, Blue Gene Q, at Lawrence Livermore National Lab. It's called Sequoia. It has 96 racks, 1.5 million processors, 1.5 petabytes of main memory, 6.3 million threads, and we have run a simulation of the True North architecture at a scale of 100 trillion synapses, which is essentially the same scale as the number of synapses in the human brain. However, the simulation runs about 1,000 times slower than real time. So you can see that it's orders and orders and orders of more magnitude to simulate brain-like computation on today's the best and the greatest computers. And therefore, we're continuing with the quest to realize True North in silicon. And this shows you how the architecture that we are building essentially can be realized in silicon. This is the same wiring diagram that we derived from the primate brain. And instead of each of the brain regions Imagine a network of true north cores, all interconnected in a biologically realistic fashion with biologically relevant neuron behaviors. This is a substrate on which we can create a huge variety of applications, applications that have power to transform science, technology, government, business, and society. What you see in my background, perhaps not very clearly, is BrainWall. It's a display that we created with 64 million pixels, which we call it rat scale because the rat brain has about 64 million neurons. And to summarize, what we have done is we have developed an entirely new vertically integrated technology stack. We have started with supercomputing simulators. We've collected data from neuroscience. We've simulated this data on the supercomputer at a scale of 100 trillion synapses. We've developed in silicon 45 nanometer CMOS, tiny little worm-scale neurosynaptic cores. We've created a new computer architecture as a network of these neurosynaptic cores. But imagine this. The past era of computing, the programmable computing, had two cornerstones. One was ENIAC, one of the first programmable digital computers, and then ENIAC became useful via Fortran, which taught us how to utilize ENIAC. But if you create a totally new architecture, trying to apply languages from the previous architecture to it is like fitting a square peg through a round hole. Therefore, we have invented an entirely new programming language, a programming model, which is essentially like Lego blocks. We think of each course as a Lego block, and we compose them together to create a wide variety of algorithms and applications. We've implemented about 150 algorithms on this new language, and we have demonstrated a slew of new applications. So now, let me look to the future. Conceptually, what does this technology bring to art, science, technology, society? So these are some of the conceptual models. And I hold in front of you a conceptual model that we have created that we call BrainCube. BrainCube will have capacity in terms of number of neurons and synapses of a small mammal brain. And it would consume very little power comparable to a light bulb, and yet to simulate it would require racks and racks and racks of today's computers. So what is happening is that we are entering a new era of computing where instead of bringing data, the sensor data, to the computation, we can now bring computation to the data. Therefore, the sensor becomes the computer. You can see a lot of conceptual models. You see a ball, that's a rolling search and rescue robot with active switching camera surfaces that can be rolled into a Fukushima-like disaster or a burning house to look for a pet or a child. Again, I want to emphasize these are conceptual models that we have created to create a conversation between scientists, artists, technologists. And as I conclude this talk, I would like to acknowledge the work of a very large team. This project is funded by DARPA, has brought together 6 leading universities, 1 now in Zurich, INI Labs, as well as 8 IBM labs and fabs, Almaden, Austin, Yorktown, East Fishkill, India, Japan, Rochester, Zurich, and has brought together resources from Department of Energy and collaboration from Lawrence Livermore National Lab, Lawrence Berkeley National Lab. And I also would like to thank DARPA and our program manager for their support. And these are some of the people who participated in Synapse Phase 01. These are some of the people who participated in Phase 2. And these are some of the people who are participating in Phase 3. Finally, the work has really received nice acclaim. It has been featured on the cover of Science, Communications of ACM, and Scientific American. With that, I really thank you for giving me this opportunity to present to you, and I hope you have a great symposium. Thank you. Questions?
I'm going to ask if there are any questions here that I will relay. There don't seem to be any questions at this point. Ah, over there. Let me give you the microphone.
What about the energy consumption of this?
Right. The whole project is about the energy consumption. In other words, we're trying to encapsulate brain-like computation, orders and orders and orders of magnitude less power than possible with today's von Neumann computers.
Okay, there's a second question.
So what do you think would be the difference between a human and a machine?
So these machines that we're creating are not at all comparable to humans. The question is not directed properly. See, what is happening today is that we have instrumented the earth and space with cameras, microphones, sensors. As a result, the data is coming at us like a tsunami, like a wave that we just cannot handle. A lot of this data is write once, never read. It needs to be analyzed at the source of production rather than afterwards like we do today. So these new computers give us an ability to make sense of this data, to move computation closer and closer to the source, to go and create cars that can understand their scene, or create glasses for the blind that can help them navigate a complex environment, or to endow new generation of smartphones with capability of a better interaction with us in a more natural manner. So what we are creating are systems, computer systems, cognitive systems that can understand their environment and interact with them better. Humans are the ones who consume this technology.
And we have a final question here.
As you know, the European Human Brain Project also uses neuromorphic computing, using connectome technology. What is the difference of your project to the Human Brain Project?
Let me give you an example. You see, once to understand how the brain works and to build computers based on that understanding is like climbing a big mountain. Let's say Mont Blanc. Now, if you've never climbed the mountain, different teams will take different paths. One will take the south face, one will take the north face, somebody will go from the west face, and so forth. But once you climb the mountain and you look down, you see the unity and diversity of all these paths and the necessity of it. So that's the same paradigm here. We face today an insurmountable looking challenge to understand the brain and to build computers based on it. And in this complex mountain that needs to be scaled, it is really a virtue that a lot of different people are attacking it from lots of different angles. And we hope that somebody will succeed, and we as a society, as a civilization, as the planet will all benefit. So once again, I thank you for giving me the opportunity to talk to you and for your thoughtful questions. Thank you.